dependence of equilibrium constants. So previous class we were talking that the mode of representations, mode of representation of reactions, how it affect the equilibrium constants. So we discussed about the theories. So now we are basically going to discuss the examples regarding these types of problems. So we have, so we were stopped from here. So what here, this example, what says CO gas plus half O2 gas, that is going to give CO2 gas, and this is K1, and 2 CO gas plus O2 gas, and this is going to give 2 CO2 gas. This, so what is the value of this? So they asked that what is the relationship between K1 and K2. So what they did, just multiplied by a factor 2 to both the in the balanced chemical equations. So if we multiplied a factor to a balanced equations, then then that will affect the equilibrium constant by a factor of that, that will be get raised to the power of that factor. So here the K2, so this same chemical equations, what you do, just multiply it by a factor of 2. So if you multiply by a factor of 2, then that factors get power, so that will be 2. So where it says K1 square equal to K2, so this K1 square equal to K2, so option D. So similar examples regarding on mode of representation of reactions, how it affects the equilibrium constants. So here the first equations, if you observe carefully in these equations, so they given the three reactions and they ask the relationship between the equilibrium constant. So for this reactions A they given K1, and for reactions 2 they given equilibrium constant K2, and for reactions 3 they given equilibrium constant K3. So what is the relationship between K1, K2 and K3? So what they did, if you look this carefully, what they did, they add the equation 1 and equation 2. So just add, so they what they add, equation 1, this is K1, and they add with C4 gas plus H2O gas plus 3H2 gas, and this is K2. So what they did, they add these equations. If you look carefully, the equations 3, this has come by adding these two equations, equation 1, equation 2. So what happened? This CO gas and this CO gas cancel it. So just add CH4 gas plus 2H2O that is going to give CO2 gas plus 4H2 gas. So this is K3. And what K3? So if we add the two chemical equations, what is the effect of the equilibrium constant? That will get multiplied. So this is actually what? This is actually, this whole equation is K1 into K2. And these equations they given the K3. So K3 equal to K1 into K2. So this is the relationship between the three chemical equations. So if you add, but they basically doing, they adding the equation 1, equation 2 and getting the equation 3. And so if the two equations get added, then equilibrium constant get multiplied, and this equation 3 is K3, then K3 equal to K1 into K2. So this option is correct. So mode of representations, how equilibrium mode of representation of reactions, how it affect the equilibrium constant, we studied. So next is dependence equilibrium constant, that actually depends on temperature. So it depends on the temperature. Equilibrium constant is depend on temperature. So how? Like if from Bartók equations, what it says that if you say log K2 by K1 equal to delta H 2.303, because log, then T2 by T1 into T2. What he says, what this equation says, that if for delta H equal to positive, that is endothermic reactions. Positive means heat is absorbed, that is endothermic reactions. So if delta is positive, then log K2 by K1 is greater than 0. Then K2 is greater than K1. So what it says, that if temperature increases, then K also increases. So for endothermic reactions, if temperature increases, then equilibrium constant also increases. And similarly for delta H is negative, that is exothermic reactions, heat is releasing, then that is exothermic reactions. So here, so log K2 by K1 is less than 0, that is log K2 minus log K1 is greater than 0, that is K1. So what says, if temperature increases, then K decreases for exothermic reactions. And if delta H is 0, then log K2 by K1 equal to 0. Then that is K2 equal to K1. So if temperature increases or temperature decreases, K will remain constant. So if delta H is 0, on that case, whether you increase temperature or decreases, K remain constant. So this is the dependence of equilibrium constants on temperature. So how equilibrium constant is affected by increasing or decreasing temperatures? These are the three things we said. So that is depend on the enthalpy. So enthalpy is positive. If enthalpy is positive, then if temperature increases, then equilibrium constant also increases. And if and delta H is negative, enthalpy is negative, then if temperature increases, then equilibrium constant decreases. And for if enthalpy delta H is 0, then either if increase temperature or decrease temperatures can remain constant. So that is the dependence of equilibrium constants on temperature. And third, equilibrium constants depends on so next we will study the equilibrium does not depend. So equilibrium constants does not depends. One is catalyst. So if you add the catalyst, then what the catalyst is doing? It increasing both forward reactions and backward reactions. So overall it is helps to achieve the equilibrium quickly. So it does not affect the equilibrium constant because it helps both the forward and backward reactions. It not only, so it does not affect only one, that is forward reactions or backward, it affects both. So a catalyst, if you add the catalyst, then it enhance the equilibrium, it enhances the rate of the reactions. So it achieves to equilibrium constants quickly, so it does not affect the equilibrium constant. So like if you say this time, so you know this, so this is forward and this is backward reactions, this is the rate of forward reactions, this is the rate of backward reactions. This is suppose you achieved here at this point, this is without catalyst. And if you add the catalyst, then what will happen? This increases the forward reactions, and at the same time it also increases the backward reactions, so that it achieves the equilibrium earlier. So here with catalyst, so catalyst helps the equilibriums to achieve quickly, so it does not affect the equilibrium constant. So equilibrium constant does not depend on the catalyst. So in the reactions, if you add catalyst or do not add, that will not affect the equilibrium constants. Secondly, equilibrium constant does not depend on adding inert materials. Inert materials like helium, neon, they add, then it does not affect the equilibrium constants. So, and third, equilibrium constant does not depend the initial concentrations of the reactants. So we'll solve some problems, some examples about how regarding this type of how equilibrium constant depends. So I bring some questions. Okay, so this for a reactions H2 and I2, that's giving 2HI, the combustion reactions. So for the equilibrium constant Kp changes with total pressures, Kp will change by total pressures, amount of H2 or I2 presents, catalyst or temperature. So Kp only changes with temperature. It does not change by catalyst. It does not affected by the reactants. It does not affected by the total pressure. So it only affected by the temperature. Or this example, at constant temperature, the equilibrium constant Kp for the decompositions of reactions N2O4 that gives 2NO2 is expressed by Kp equal to this, where P is a pressure, X is extent of decomposition. Which of the following statement is true? So Kp is increased with increasing pressure, Kp is increased with decrease of X, Kp is increased with increase of X, Kp remain constant with change in P or X. So Kp only depend, Kp or Kc or equilibrium constant. This is one. So these only depend on temperature. So this remain constant with change in P or X. So this is wrong, this is wrong, this is wrong. Another questions, consider the following equilibrium equilibrium closed container. This at a fixed temperature, the volume of the reaction contains is halved. But this change, which of the following statements hold true regarding the equilibrium constant Kp and degree of dissociation? Okay, so when that volume is getting half, then what will happen? This is the degree of dissociations. We will study. So we will study later. So this will change. So both Kp and alpha change. No, alpha will, so Kp only change if temperature is changes. So this says that they do not change, do not talk anything about of temperature. So Kp will not change. So Kp does not change, but alpha will change. Yes, Kp does not change, but alpha will change. Kp changes, no. Neither Kp nor Kp changes, no. Alpha can change. So option D is correct. Next reactions, next examples. Pure ammonia is placed in a vessel at a temperature where its dissociation constant alpha is appreciably at equilibrium. The true statement is this: Kp does not change with pressure. Yes. Alpha does not change with pressure. No, alpha change. Concentration of NH3 does not change with pressure. No, it will change. Concentration of hydrogen less than that with hydrogen. No. So option A is correct. So Kp or Kc, that is equilibrium constant. So we know that equilibrium constant that is Ke can expressed as Kc or Kp. This is for both liquid and gases. This is for only for gases. So this and this will only change with temperature and is not affected by the pressures, the concentrations, and etc.